let's start today's class. So, as usual, I will very briefly recall whatever we have done in the previous class. So, in the previous class, we have learned the concept of equilibrium in a game theory. So, as we have discussed in the previous class, uh, it is so in the in this series of classes we have learned that how to how we can mathematically represent a strategic interaction, where strategic interaction by means of until now we have it is on this point in this point it is clear that strategic interaction means where the outcome does not the outcome not only depends on the action of the individual but also depend on the actions of other individuals who are present or who take parts to create that outcome. And game theory is a mathematical way to represent that kind of strategic interaction, and it is required in game theory. Obviously, the solution of a strategic interaction is required to predict or prescribe the outcome of the strategic interaction, and we have searched for that solution. And we in the previous class we have introduced a concept of solution which is known as Nash equilibrium. And why this concept is called equilibrium? Because if we go to the definition of the Nash equilibrium, we will see, let's see definition of the Nash equilibrium. So we have basically introduced here the pure Nash equilibrium, pure Nash equilibrium. And what does it mean? We are searching for a action profile, a pure action profile, which means it prescribes this action profile prescribes actions for each player. Suppose there are n player present in strategic interactions, so Nash equilibrium is an action profile, that means it associate a action with every n player such that when we see in terms of utility, for every player utility we will see that every player's utility is optimal in this action profile, given that other players are stick to their actions. That means here this action profile is equilibrium in a sense that if all the individuals adopted this equilibrium, then there will be no other actions for any individual I if she or he deviates from that prescribed action by Nash equilibrium from ai to any other action ai prime, that individual will not benefited by such deviation. So if all the individual remain in Nash equilibrium, there will be no incentive to unilaterally deviation from the Nash equilibrium for gaining his or her utility. So that is a Nash equilibrium, because if all the individuals it's correspond means it's is analogous to a steady state situation. If all the individuals are in the steady state, then no one will want to deviate from the steady state, they will remain in the steady. So the Nash equilibrium basically a steady state like concept. And we have seen only the when individuals are taking pure action, that means if n actions are available, then our individual will take one action among that n action. Now we have also seen the Nash equilibrium for the games that we have presented earlier. So we have seen that what is the Nash equilibrium for prisoner dilemma, and we have seen that this game captures this game as well as the Nash Equilibrium in this game captures the free riding that individuals free riding makes them to choose the worst option possible, even though. So here this thing where both of them will confess and will get a punishment for um, for 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 longer amount of time than when, whereas there available optimal solution or a solution which I will not say optimal, but I will say there is a solution exists better than this Nash equilibrium for both of them. However, the free riding tendency, out of the fear of free riding, everyone will want to stick with the strategy that is to confess, that is thing, and that is the worst outcome possible. So this is a dilemma situation where although individual can be beneficial, there is some outcome which is beneficial for both of them, but they don't want to change their strategy together. So in this situation there is no individual wants to unilaterally deviate from whatever she is from the confessing the crime. So that the situation. Now in the second, this is called prisoner dilemma. Now in the case of battle of sexes, we have seen that two Nash equilibrium present, and this shows that Nash equilibrium is not unique. So it is in the definition of the Nash equilibrium, it is not says anything about the uniqueness of the Nash equilibrium. For a single game like battle of sexes, there can be multiple Nash equilibrium. And also we have seen a game where the in the definition of the Nash equilibrium, it is also not guaranteed that there the existence of the Nash equilibrium. So that means we find this matching penny shows a example of game where we have find no pure Nash equilibrium. That means in this game there is no pure strategy Nash equilibrium. Now we have also seen likewise the battle of sex game. There is another game, it is called stack hunt game, and in this stack hunt game also there are two Nash equilibrium present. Now we will in this class we will see another situation that is called the hawk tub game. And we will calculate the Nash first pure Nash equilibrium of the hawk tub game. So let me go back to the previous class and let's see that what is the payoff of hawk tub game. What is here? I think it is here actually. So hawk tub payoff of the hawk tub game is -1 -1 1 2 2 1 0 0. Okay. So this game will be represented by hawk strategy. And as we have discussed in the previous class, this hawk strategy means a aggressive strategy and dove strategy means the passive strategy. This is -1 -1, then this is 0 0, this is 1 2, this is 2 1. Now let's see what are the Nash equilibrium here. Does this hawk strategy is Nash? So let's see the utility of player 1 while playing hawk is -1. Now we have to ask the question, is the does player 1 has any incentive to deviate from hawk when the other player is adopting the strategy hawk? So we have to check what is the utility of playing the strategy dove stock. So that will give player 1, that will gives player 1 a pair of +1. So that means by changing from hawk to dove when the player 2 is playing hawk, always uh, always gives player 1 a better utility. So that means there is always incentive to change from hawk to dove. So that is this strategy is not a Nash equilibrium, since there is an incentive change of player 1 from this strategy unilaterally, so not a Nash equilibrium. And similarly one can check for the player 1 also. If you see for player 2, you also see that player 2 in the hawk strategy, player 2 also getting -1, and if player 2 also change from hawk to dove, it will also get a pair of +1. So that means there is always that means always wants to change her strategy from hawk to dove. Now if I see the different situations, that is there any incentive if the player 1 choose from so let me see the another situation. Is this action profile dove okay is Nash equilibrium? Let's see. The utility of player 1 is 1. Does player 1 wants to change from dove to hawk? No, because if it change, then it will get a pair of -1. So there is, for player 1 there is no incentive to change. Let's see for the player 2. Player 2 is getting 2, so obviously in hawk both or both of them will get -1. So obviously there is no incentive for changing the strategy from dove to hawk. So that means if this strategy and the dove, this action profile dove comma hawk is a Nash equilibrium, since there is no incentive to deviate from this. So this is a Nash equilibrium. So Nash equilibrium. Now you will find the similar situation for the case of that hawk dove. Here it will get 2, and if player 1 change from hawk dove to dove, it will get a pair of 0. So obviously it loses in terms of utility. So player 1 don't want to change from hawk to dove. Now let's see for player 2 also. Hawk dove, it will give him +1. Now if it change from dove to hawk, it will give him -1. So it will not change because it will lose its utility. So that means this strategy profile also a Nash equilibrium, because no individuals wants to deviate from this strategy unilaterally, and we'll see that dub is again is not an Nash equilibrium. Why? You see dub will give him 1, but player 1 can do better by playing hawk against dub, so there will be always an incentive to change from this strategy. Now similarly for player 2 also, there is a better option by playing, obviously there is a better choice to play hawk against dub. It will give him objective, so there is always incentive to changing from this strategy, this action profile. So this is not a Nash equilibrium. So we see that likewise the stag hunt and battle of sex games, we have seen here also case of hawk dub game, there exists two Nash equilibrium which is corresponding to one playing hawk, another play dub, and the vice versa, that the player 1 plays dub and the player 2 plays the hawk strategy. Now we will go to the question that is there is some way from which we can get a Nash equilibrium for the situation like matching pennies game? Is there any possible solution? So you want to now see, is there any possible equilibrium situation now? To answer this, we have to focus to a point that whenever we are discussing, we are talking about in terms of pure strategy. That means the player 1 or 2 either choose the action, suppose there is m action available, so the player 1 or 2 or any player will choose one action with certainty. We are not talking about that any uncertainty involved of a player 1's action itself. So what do I mean by that? So I am suggesting that why not the player 1 randomize the action available, why only choose the deterministic strategy? I am saying that why not in the matching penny situation, player 1, since there is no way to choose a best action, so why not maximize some point of time I will choose head, some point of time I will choose tail. So in that way, in some sense, so I will in some time I will get a positive utility, and sometime I will get a negative utility. That means in sometimes I will get 1 rupees and sometimes I have to pay 1 rupees. So that means I am suggesting why not player 1 is randomize his strategy according to, suppose with probability p, it shows that player 1 shows the head, or rest of the time, and the rest of the time it shows tail. Why not this kind of strategy we are adapting? Now when we will adapting this type of strategy, it will no longer a pure strategy, rather it will become mixed strategy or stochastic strategy. So in the literature of game, it is always called the mixed strategy. So now we will talk about the question. We will change the question slightly such that it become is. So we already know that for the matching pennies, for the game like matching pennies, there is no equilibrium, no pure Nash equilibrium. So now we are asking the question, is there any mixed equilibrium? That means we are wanting to explore whether or not there exists a strategy or strategy profile uh, which corresponds the probability of playing action. Suppose here the strategy profile, suppose uh, with probability p player 1 plays head, and with probability 1 minus p player plays tail. And so I am talking about this is so I am talking about so a strategy profile, suppose a star or alpha star equal to, suppose alpha 1 for player 1 and alpha 2 for player 2, where alpha 1 is a vector corresponding to p, 1 minus p, which denotes the probability distribution of player 1 over his action, and alpha 2 is again suppose q 1 minus q, which represent the probability distribution over player 2's action. So is there exist any mixed equilibrium? So to seek the answer, we have to use the concept of VNM expected utility theory. Now we have to use now why? Because here now you can see that the uncertainty faced by the player 1 can be represented in terms of a lottery. Suppose this is a game. So this is a game. This is a game. Now with probability, suppose q 1 minus q, the player 2 is playing head tail. So when player 1 will the for the player 1, the option head becomes a lottery, where with probability q it will get +1, and with probability 1 minus q it will get -1. And similarly tail also becomes a lottery, with probability -1 it will get a pair of -1, and with probability +1 it will get, with probability 1 minus q it will get +1. So that means the head and tail now becomes not the certain options, but becomes a lottery. Now the individual has to prefer among the lotteries, and we have seen that if we assume that players are VNM rational, then we can use the expected utility to represent their true preference. Now we want to stick with that notion that the players are VNM rational. In the next class, probably in the next class, we will see a concept where the players are not VNM rational but the procedural rational or bounded rational that we have presented earlier. For this case, we will see that the players utility in a lottery situation can be represented in other way or other than in rather than VNM expected utility. Now let us see that is there any equilibrium or is there any steady state if all the individual are taking that action, anyone don't want to change from that action, is there exists such action or not. So let's see that. Now let's see and such. Now let's see that whether or not the whether or not the so now here my claim is that uh, my claim is here the equilibrium exists and it corresponds to every players every players every player or each player chooses each of her actions with probability of. Suppose that player 2 suppose that player 2 chooses her action head and tail with probability half and half. Now if player 1 chooses action head with probability p and tail with probability 1 minus p, then let's see with which probability that player 1 will get 1 rupees. So with which probability it will get 1 rupees, because so let's see the outcomes. So that means the outcomes head, that means player 1 is playing here and player 2 also playing head, will come with which probability half into p, and similarly head comma tail with probability half into 1 minus p, and in this situation it will get +1, in this situation it have to give -1. Similarly this situation also, this outcome will occur with probability half 1 minus p, and this tail comma head this will occur with probability half into p. So in particular, the probability distribution over in particular, that means with which probability player 1 gain plus 1 rupees, gain plus 1 rupees, player 1, with which probability it will get half p plus half 1 minus p, it will equal to half. And similarly, lose minus 1 with probability will see that half into 1 minus p plus half into p equal to half. So you see the outcome of player 1, that means getting plus 1 or minus 1, does not depend on p. That means if player 1, if does not depend on, so here you can see that gaining or losing 1 rupees, the probability of gaining and losing plus 1 rupees, so that means player 1 will see his option, whatever in whichever way he randomizes his action, he will see the outcomes as a lottery, that is that it will gain with probability half and lose with probability minus half. So these outcomes are independent of p. So which means independent of p, so that means so each p is a so that means each p or every p is optimal, every p is optimal. Or another way we can say that in particular player 1 can do no better than choose head and tail with probability because every in every probability, whatever probability it is, including half, the all probability seems, the all action seems equally better, or every action will give him the same lottery. So with probability whatever action the player 1 choose, that every action will give him the same lottery. The lottery is with half probability it will gain, and with half probability it will lose. So that means, so half, that if it randomizes his strategy half up, it is equally better. So there will be no incentive to change from half to any other strategy to gain. Now if we consider the same situation for the player 2 also, when player 1 chooses the action, each action with probability half, then we conclude that player 2, when the same situation, similarly when player 1 is choosing her action head with probability half and tail with half, then the same situation will be faced by player 2. That the player 2 will find that his player 2 find that his outcome is independent of his action or strategy. So that means for the player 2, for every choice the outcomes are the lottery. With probability half it will gain, and with probability half it will lose 1 rupee. So that means for player 2 will also find that that there will be no incentive for player 2 to change your strategy, that is playing head with half and playing tail with half. So change her strategy. There is no incentive of player 2 also to change her strategy from half up. And if she change, even there is no incentive, because if she change, she can do no better if it change from half up. So that is what is equilibrium means. So if both of them will adapt the strategy, that will they both of them mix their strategy with probability half up, no one wants to deviate from their strategy. So this is shows that there exists a equilibrium. Now if one can say no, we can in this, if I follow the same logic, then we can say that any action profile is a Nash equilibrium. So let's see that what this is not in general true. So suppose that with that player 1 strategies with probability with p, it will with probability p it will play head, and with probability 1 minus p it will play tail for player 1, and similarly for player 2 with probability q it will play head, and with probability 1 minus q it will play tail. Now in this situation let us calculate what are the outcome. Now similarly, what will be the probability of coming head head? That will be pq. What will be the outcome of head tail? That is p 1 minus q. What is the tail? That is exactly 1 minus p into 1 minus q. What is the probability tail head? So that is 1 minus p and q. Now we know that what are the outcomes in which player 1 will get. If I see these things for them from the player 1's perspective, in the player 1 for the matching pennies game, we know that player 1 will player will gain 1 rupees in these two situations, and it will lose 1 rupees in these two situations. So what is the probability that it will get plus 1 rupees? So it will get plus 1 rupees in this situation, pq plus 1 minus q 1 minus q. If I simplify this, it will become pq plus 1 minus q minus p plus pq. So this is 1 minus q plus p 2pq. So I take p common, 2q minus 1. So here player 1 will get plus 1 rupees with this probability, and with which probability it will lose 1 rupees. So in if I add these two probability, you will get that p1 minus q plus 1 minus p into q, that will be so q minus pq plus p minus pq. So this will be q plus p1 minus 2q. Now if you see, so this is a lottery. So for the player 1, the outcome is a lottery with probability 1 minus q plus p into 1 minus q 2q minus 1. So with this probability it will get plus 1, and with probability q plus p plus 1 minus 2q it will get minus 1. So as we know from the von Neumann Morgenstein utility theory, that any agent who is VNM rational or who follows the axiom, it will always prefer a lottery whose whose if since here means if any individual will prefer a lottery from this whose the probability of getting plus 1 is higher. So let us see one situation, that if q is less than half, then what is the situation? If q is less than half, obviously this is a positive term, or this is a negative term. So if q is half, then for q is less than half, you will see that 1 minus q, so 2q, so this implies that 2q minus 1 is less than 0. So this will become p into some function of fq. Now if you see this situation, you will find that this is a decreasing function of p. So if p decreases, it will increase, the probability will increase. So if p decrease, the probability will increase of getting plus 1 rupees. So a individual who is VNM rational always want a lottery whose means in which getting plus 1 rupees will higher. So that means it will choose p which give him the plus 1 rupees with maximum probability, and which is that means it is a decreasing function. So player in this case, if q less than 2, q less than half, player 1 always tries to choose p equal to 0, because always wants to decreasing p and corresponding to p equal to 0. So in for every p, if q less than half, for every p there is, for the player 1 there is an incentive to decrease the p and choose the strategy corresponding to p equal to 0. And the similar situation will occur, if you see similar situation, it will occur when q is greater than half. When q is greater than half, this will corresponding to 2q minus 1 is greater than 0, and these become a increasing function of p, and the individual wants to change or deviate from the strategy, any strategy p, to p equal to 1. So any strategy corresponding to q less than half and p not equal to 0 is not a Nash equilibrium. Q less than half and p not equal to 0 is not a Nash equilibrium, because there is incentive of deviating from that strategy, and obviously p greater than half also, and p not equal to 1 is not a Nash equilibrium. Now you will find the same situation when we will see that p is for the p is greater than half and p less than half also, we will find the same situation for player 2. For player 2, you will find that for p greater than half, for player 2 the best choice will be q equal to 0, and for p less than half, for player 2 you will see that player 2 whose base choice is corresponding to q equal to 1. So that is, there is, so the all the other strategies is not Nash equilibrium, because in all the other strategies either player both of the player and player 2 has incentive to deviate from that strategy. So in other strategy, in other than p equal to half and q equal to half, other than p equal to half, which is we have shown that is a corresponding to steady state, or in all other strategies player 2s have a clear player both each player has clear incentive to deviate unilaterally from that strategy, and from p equal to half and q equal to half there is no player has any incentive to change from that strategy unilaterally, because no player will gain by doing so. Now let us present the concept of mixed Nash equilibrium. Then I will calculate the mixed Nash equilibrium for each game that we have presented using presented. So let us present what is the concept of mixed Nash equilibrium. Mixed strategy Nash equilibrium. So a mixed strategy so a action profile is a mixed strategy Nash equilibrium. A mixed action profile obviously is a suppose alpha star if the expected payoff player I if in alpha star is at least as large as the expected payoff to AI of any other strategy AI that A minus I alpha star. So when all the other individuals are stick to their prescribed the Nash equilibrium this alpha star strategy, Nash equilibrium strategy, and the other than the Nash equilibrium prescribed strategy, that is alpha I, then this condition that the expected utility that is that player I is getting by playing the strategy prescribed by Nash equilibrium should be at least at higher than any other strategy when others stick to their Nash equilibrium. So that means UI expected utility of alpha star is has to be greater than equal to UI any other strategy alpha I, and this is alpha minus I means the rest of the other strategy for every strategy alpha I of player I. So here you see that since that any other strategy cannot give larger payoff than what it is getting by playing the Nash equilibrium strategy, so there will be no incentive to change unilaterally. So as we have discussed in the case of case of matching pennies game, where the playing head and tail with probability half half for the both player is a Nash equilibrium. Why? Because no other player, no other strategy, when one player is playing with probability half, no other player can do better. It will get equal if it choose other strategy. So if it can do no better by playing other strategy than playing the probability with half. So this is the definition of the Nash equilibrium. Now we will see how one can in general find out the Nash equilibrium. So it is called the base response function. By constructing base response function, now we will see that with the base response function there is a connection with the Nash equilibrium. So base response function will be denoted by, suppose I player's base response will be Pi, and for a strategic game with ordinal privacy, so base response of Bi, that means what is the base response of player I when the other player are adopting a strategy alpha prescribed by action profile alpha I. So is the set of is B is the set of player I's best mixed strategies is when the least when the list of other players means strategy is alpha minus I. From the definition of a mixed strategy equilibrium, a profile alpha star of the mixed strategies is a mixed strategy Nash equilibrium if and only if every player's mixed strategy is the best response to other players. So this is the concept, because best response means in the response where it will get a higher payoff. And if you see from here, that here everyone's getting in sense of optimal when others are when the if we fix the other strategy. Now in the particular here in the Nash equilibrium, in the both pure strategy and mixed strategy Nash equilibrium, you will find one thing, that is in the both cases the Nash equilibrium strategy is based to, so if alpha I star is the is a strategy that is prescribed for individual I in the Nash equilibrium, then alpha high, the strategy alpha star has to be best response against all the other strategy. Why? If it is not best response, then that means there exists another strategy alpha high, in which you will get higher expected utility than alpha star. And if it is so, then alpha star will no longer be the Nash equilibrium, because it is by definition, if alpha star is a Nash equilibrium, the utility should be maximum. If utility should be such that no other alpha I can give the payoff higher than what you will get by alpha star. So since alpha star here is the best response, means it will give, means no other alpha I exist which will give the player one as much means higher expected utility than that it is getting from by playing alpha star. Now if we can see the base response function, then we can calculate the Nash equilibrium. So let us see the example for the matching pennies game of this. Then we will get an idea what the base response function looks like. Okay, for again matching pennies game. Okay, matching pennies game. So you know the matching pennies game is head, tail, head. This is tail. This 1 minus 1, this is minus 1 1, this is minus 1 1, this is 1 minus 1. Now if you think about the situation where the player 2 playing head with quality q and tail with quality 1 minus q, and player 1 playing head with quality p and displaying 1 minus q as 1 minus p. Now let's see what are the base responses. So what player 1 will get by playing head? Okay, yes, by playing it, what expected utility it will get if it play head. So player wants player wants expected utility for head. What is that? If I calculate, so if it plays head with probability q, it will get 1, and with probability 1 minus q, it will get a 1 minus q. So that means expected utility is q plus q minus 1, that means 2q minus 1. And similarly, what is the expected utility? Expected utility for tail, that is q into minus 1 plus 1 minus q into plus 1, so that will be 1 minus 2q. Now if you think about the situation, now we can calculate the base response. So base response function of 1 against the strategy q will be 0. So when the 0 will be base response, as we have seen in the previous example also, when q will be less than half. If q is less than half, why? You can see from here, for q less than half, by playing tail it will get a positive utility, while by playing tail it will get a positive utility, whereas this means 1 minus 2q is less than 0. So that means, no, I am wrong. So 1 minus, so this means 1 minus 2q is greater than 0. So that means by playing head it will get a positive utility, whereas by playing tail, sorry, let me rephrase it. It means if q less than half, it means by playing tail it will get 1 minus 2q, that means a positive number, that means 2q minus 1 is a negative number. So that means for q less than half it will get a positive utility by playing tail, and it will get a negative utility by playing head. So that's why it will never means the base response for q less than half to play tail, by playing tail it will get a positive utility. Similarly, by playing head for q greater than half, for let me rephrase it in this way. For 1, if q is greater than half, this means 2q minus 1 is greater than 0, that means 1 minus 2q is less than 0. So this means in this situation, if q greater than half, then player 1's base response should be playing head, because by playing head it will get a positive utility, whereas by playing tail it will get a negative utility. So in this case, for q greater than half, the base response will be playing head. Now if one case remains for q equal to half, as we have seen, for q equal to half, playing any p, that is any p which is in between 0 to 1. So every p which remain between 0 to 1 is a base response. Why it is a base response? Because you will see for q equal to half, both of these expected utility is 0. Both of these expected utility is 0. So that means whatever way the player wants can play, it cannot do better by playing any other actions. In every action it will get a pay of 0. So that means every action is the base response. That means every action will give him or her the equal payoff. Now we can write the same thing for this is the base response function. Now the same thing we can write for the player 2 also. Now we will see for player 2 this is 1. So this set is 1 if p is less than half, and similarly q equal to any, because in this situation when p equal to half, every q will for the every q the expected utility will be 0. So the every q will give him the same payoff. So that is why every q is the base response, and for p greater than half, the only by playing tail is the only base response. So now we can graphically represent it, the base response functions. Suppose this is this is suppose 1, this is 1, this is 0. Suppose this is half, this is half. Now suppose this represent probability p, these represent the probability q. Now let's write the base response function, which is a base response of player 1, which is a function of q. So when q less than 1, the base response is p equal to p corresponding to 0. So that means base response is this. And for every q less than half, the base response is that p equal to 0. When q equal to half, for q equal to half, every p is the base response. So that means every p is the base response. So every p is the base response. So this is the base response. Now when q greater than half, for every q greater than half, what is the base response? The base response is only one thing, that is q equal to p equal to 1. So that is p equal to 1 is the base response for every q. So for every q, p equal to 1 is the base response. So this is the base response function of player 1, which is a function of q. Now what will be the base response function of the player 2, so player 2, that means for less than uh, for less than p equal to for less than p equal to half, for every less than p equal to half, it is for every less than p equal to half, the q equal to 1 is the base response, and for half it is every possible action, every q is the base response. Now, and for p greater than half, only q equal to 0 is the base response. For every p greater than half, so 0 is the base response. So here this is base response function p2 v2. Now, what is the Nash equilibrium here? Nash equilibrium corresponds to where the two base response meet. So this point is corresponding to Nash equilibrium. Is corresponding to Nash equilibrium, which is p equal to half and q equal to half. Why this is Nash equilibrium? Because in this point, if you ask what is the base response, because this point is half, so what is the base response of half, you will get half. So this is again you will get this half. And what is the base response of player 2? If I, okay, let me put it in this way, it will be clearer, because base response of b, which is a function of q, which is equal to half, what it is the point p, which is p equal to half. And what is the base response when I will put the point p equal to half? So that is q equal to half. So that means this point is base response to itself. For every player, this point corresponding to base response to itself. So that's why it is Nash equilibrium, because it satisfies the Nash equilibrium, because by definition Nash equilibrium represent a action profile where each action has to be base response to the when the other choosing by the prescribed Nash equilibrium. So that's it. Now we will see the Nash equilibrium for battle of sex games. Now we will again do the same thing for the battle of sex games. So what is the battle of sex games? So okay, one option was cricket, another option was musical concept, music, cricket, this was music, two 1 0 0 1 2. Now if you see here, so let us see again similar way. This is q, this is 1 minus q, this is p, this is 1 minus p. What is the expected utility? Expected utility for cricket from player 1's perspective. So this is 2 into q plus 0 into 1 minus q, so that is 2q. What is the expected utility? For musical concert? So that is 0 into q. With 0 probability it will, with q probability it will get 0, and with probability 1 it will get 1 minus q, so that is 1 minus q. Now when the cricket is the base response, that means when the p equal to 1 is the base response, so let us write the base response function of 1. When the cricket will be base response, so cricket will be base response, that means if cricket is the base response, then it should be true that utility of the cricket has to be greater than utility of the music, so 2q has to be greater than 1 minus 2q. So this is equivalent to say 3q has to be greater than 1, so this is equivalent to say q has to be greater than 1/3. So then in this situation, cricket for player 1 is the base response, and when the music will be base response, music will be base response when 2q 1 minus q is greater than, the utility of music is greater than the cricket, so that means 3q will be greater than 1, so that means q is less than 1/3. Then the music will be base response, and when q become 1/3, then what will be happen? Then for q equal to 1/3, when the utility for music and cricket becomes same, that means 2q equal to 1 minus q, so then the utility of by playing music, by going to a musical concert or going to for watching a cricket match will be equivalent, that means the two utility will be same, and it will happen when q equal to 1/3. So in q equal to 1/3, for player 1, the both cricket and music will give him equal utility or equal payoff, so that means whatever way he mixes his strategy, all the strategy will give him a equal payoff, so that means every strategy is based, so that means every strategy is the base response. So we can write the base response function as in this way: base response of q is, this is 0 if 0 means p equal to 0, p equal to 0 means p equal to 0 means this is p equal to 0 means going for musical concert, so that is the base response. If q less than 1/3 equal to p, any p 0 between 0 to 1, if q equal to 1/3 and p equal to 1 if q is greater than 1/3. Similarly, one can write also the base response function. The same will be happen for the base response function of the opponent. Let's find out what will be the base response function of the opponent. For female or player 2, for player 2, if you see for the player 2, you will find that what is the expected utility for cricket. For player 2, expected utility for cricket is, if he play cricket with probability 1, with probability p it will get 1, and with probability 1 minus p it will get 0, so that means for expected utility will be p into 1 into p into 1 plus 0 into 1 minus q. So p will be the expected utility. And what will be the expected utility for music? If it play music with probability 0, it will get p. It will with probability p, it will get 0 payoff. With probability 1 minus p, it will get p of 2. So the expected utility for music will be 0 into 0 into p plus 1 minus p into 2. So that is 2 into 1 minus p. So base response function of player 2 is base response function we have to write. So we have to first find that when the expected utility for playing cricket is higher, p is higher than going to a musical concert, that is 1 minus p, that will find that 3p has to be greater than 2. So when p is greater than 2/3, then you will find that the going to cricket is higher. So that means, and similarly you will find that p is less than 2 1 minus p, then for going to musical concert will expected utility for going to musical concert will be higher than going to cricket match. So that will happen when 3p less than 2, when p less than 2/3, and we will find that at p equal to 1 minus 2p, that is 3p equal to 2, at p equal to 2/3, we will find that the expected utility for going to cricket match and going to musical concert is equal. So any p will be the base response. So now if we write the base response of player 2, which is a function of p, so this will be 0 if p less than 2/3, and any q 0 to less than 1 for p equal to 2/3, and for q equal to 1 if p is greater than 2/3. So let's see in terms of pictorially what will be the point where two base response intersect each other, and that will be the Nash equilibrium. Suppose this is 1/3, suppose this is 1/3, so this is the thing. Suppose this is 1, and this is corresponding to 1/3, this is corresponding to 2/3, this is 1/3, this is 0, this is again 1/3, this is 2/3, this is 1, and this direction is q, this direction is p. So let find the base response function of the player 1. So we know that for q equal to 0 to 1/3, for 0 to 1/3 base response function of 1, 0 to 1/3, q less than 1/3, the base response function is p equal to 0. So p equal to 0, then at q equal to 1/3, all values are base response, and for q greater than 2/3, only p equal to 1 is the base response. So this is the thing. Now for player 2, let's see, for the player 2, the situation is that for the player 2, when p when p less than 2/3, so up to these it is 0, so player for up to these, so p equal to 0 to 2/3, p less than 2/3, the best response function is q equal to 0, and in 2/3 all the possible values of q is the base response function. So that is why for 2/3 any value of q, any value of q, any value of q is base response function, and p greater than 2/3 only p equal to 1 is the base response. So sorry, q equal to 1 for p greater than 2/3 only q equal to 1 is the base response. So that is how. Now you can see that it crosses 3 point, one is corresponding to where p equal to 1 and q equal to 1, one is corresponding to this point is corresponding to p equal to 2/3 and q equal to 1/3, and this corresponding to p equal to 0, q equal to 0. Now we can see that from the base response function we can find all the Nash equilibrium here. In the previous section we have seen that for the battle of sexes game, these two pure is corresponding to Nash equilibrium, so both are going to musical concert and both are going to going to musical concert and both are going to cricket match is a Nash equilibrium. However, we have here seen that there is another Nash equilibrium which is mixed Nash equilibrium, which corresponding to about 2/3 time male will go to see a cricket match, and about 1/3 probability player one, that is female, is going to see a cricket match. Now why it is so? Because we have to show that this point is corresponding to such point the best response of player 1 in 1/3 is 2/3. Why? In the best response, so yes, 2/3 is the best response, because if you see for the 1/3, if I put 1/3, any value of p is the base response, so that means 2/3 is the base response, so that is true. And we have to also find that base response of 2/3 has to be 1/3. Yes, the base response of corresponding to 2/3 is any value of q, so 1/3 is also a base response. So that means this corresponding mix point is corresponding to the intersection point is corresponding to action profile, which has the property that here that every strategy is base response to the strategy which is adopted by the others. Now similarly we can calculate the mixed strategy is for mixed strategies for stag hunt game and hog dove game, and we will not calculate this situation here. Only one thing I want to point out, that you should notice that, so this is a general tendency, and this tendency is that the mixed Nash equilibrium will always be a non-strict equilibrium, because here only the equality sign follows, and this property we can use to calculate Nash equilibrium. And we can see from here, so we can calculate the Nash equilibrium by first calculating the expected utility. So if I go back here and start from here, so first you will calculate the expected utility for each action, and in the Nash equilibrium these two utilities should be equal. So we find that it is equal at q equal to 1/3, and we know that q equal to 1/3 is a Nash equilibrium. And what is the value of p? So for that you have to equate the expected utility of the player 2 and calculate in which point of p these two values are equal, you will find that p equal to 2/3, that those two values are equal, and p equal to 2/3 and q equal to 1/3 is the Nash equilibrium. So that's how in general one can calculate the Nash equilibrium by equating the expected utility, and by solving that from the equality, the probability that will get by solving those equality equation will give you the Nash equilibrium. Now we will end the discussion of Nash equilibrium today's class. Before ending this class, I want to mention one crucial point, that that there is not enough time in this course, so that's why we cannot introduce every concept, but this very important concept. One is strictness. Strictness means where these where these strictly where the Nash equilibrium action profile alpha state is such that any other action alpha I which is not prescribed by this action profile, when other are strict to Nash, is strictly lesser than the action profile Nash. So this is called the mix. This is called the strictness. But if these holds, this is also a Nash equilibrium. This is called the non-strict Nash equilibrium, and we find that the mixed Nash is not a mixed Nash equilibrium is not a strict Nash equilibrium. Why? We find that in the mixed Nash, in the action profile, each action will give the equal outcome, equal expected utility. So that's why it's a non-strict, or it's not a strict Nash equilibrium. So that's all for the today's class. In the next class we will see that if we deviate from this concept of VNM utility and adapt the concept that we introduce in the section of where we have talked about or discussed about utility, a concept called procedural rationality or stochastic utility. We using that concept, we will introduce the solution concept for the game, which is known as the sampling equilibrium. In the next class we will introduce the sampling equilibrium. So that's it for the today's class.